Hello, everyone, and welcome to this talk. I'm Alexander Kliesch. I'm from Technical University of Munich, and we will talk today about hybrid quantum classical algorithms for approximate graph coloring at TQC 2021. And this is joint work with Sergey Bravyi, Koenig and Eugene Tang. And what I will talk about today is the problem of so-called approximate graph coloring. Graph coloring is a very well-known problem where we try to assign colors to a graph, to the vertices of a graph, such that the edges, like the vertices at the end of each edge, should not have the same color. And in the approximate version, we try to minimize the number of edges for which this does not hold. And let me first give you a very brief introduction to combinatorial optimization and approximation algorithms. So first of all, we have some combinatorial function, which is defined on strings of with elements from 0 to k-1, and it should output some value r. And the goal is to maximize the value of this. And oftentimes these are NP-hard problems. And unless p equals np, there is no polynomial time algorithm for the exact solution. But what we do then is we change our focus a little. We still require efficient algorithms, but instead of only accepting the exact solution, we are happy with a solution which is kinda good. And these are so-called approximation algorithms. And the quality of such an approximation algorithm is captured by its so-called approximation ratio. And the approximation ratio tells us, for some instance, the ratio between the value of the algorithm, of the output of the algorithm, and oftentimes we have randomized algorithms, which this is the reason why we oftentimes take the expected value, divided by the actual maximal value, which we cannot really know because otherwise we would solve the problem. And the higher the approximation ratio, which is between 0 and 1, the better the approximation algorithm. And so for graph coloring, well, as I've already mentioned, so we're given some graph and we are given some number of colors. And so I've already explained what this problem is, that we want to color the vertices in such a way such that the endpoints of an edge do not share the same color. But oftentimes, if we fix the k, this is not really possible exactly. And an approximation algorithm for this problem tries to minimize the number of edges that this does not hold. And this can be modeled via this cost function here, which we actually wish to maximize. So this captures the number of vertices, the number of edges which are actually satisfying this condition. And this combinatorial optimization problem is called MaxKCut. And for example, here we are given some graph, and we this here, for example, would be a MaxKCut because there is actually no way to color each vertex with either 0, 1, or 2, such that the edges such that the vertices of each edge have different colors. However, we can find one where only this red edge here is not satisfied. And now for MaxKCut, for this problem, we do have some classical approximation algorithms. Well, it's known that it's NP-complete, and therefore we do need, in fact, approximation algorithms. And this problem is simply called the MaxKCut problem for k equals 2. And this here is a small, these are some examples for classical approximation algorithms. And the ones which we will focus on mostly in the end are, so this here is the so-called trivial algorithm, which means that what we do is we simply assign to each vertex some random color, and its expected approximation ratio is then 1 minus 1 over k. You can, for example, easily see if k equals 2, then you will see that 50% of all edges will satisfy the requirements in expectation. And the last algorithm is the one by Newman in 2018 for the case k equals 3, which we'll take a deeper look at later, which actually achieves an approximation ratio of 0.836. And now the obvious question for us as quantum researchers is, can quantum algorithms do better? And in our work, we investigate this question, and we first show that if we take the most famous approximation algorithm in the quantum realm, the so-called QAOA, which stands for Quantum Approximate Optimization Algorithm, and if we take this algorithm and apply it to the MaxKCut problem, then we see that it has there are some limitations if we do not choose the parameter of QAOA accordingly to our problem size. This is actually already well known for the case k equals 2, but we generalize it to a higher level k. And then we show that there is another limitation of QAOA, which is also shared by the k equals 2 case, namely that its lowest level version, the level 1 QAOA, can actually efficiently classically simulate it, which means that there is no actual chance of a quantum advantage for this, because, well, we can simply run the classical simulation. So faced with these limitations, and so one major limitation of QAOA is its so-called locality. And in order to sidestep this locality, we have recently, we have defined in a previous work the so-called RQAOA or recursive QAOA. And I will talk about this later, and we will extend it to the general MaxKCut case. And in the end, we will take a look at some numerical experiments. We will actually take a look at our simulations and compare level 1 RQAOA with level 1 QAOA and the best classical algorithms, which is the one by Newman mentioned before. So let's start with the limitations. So first of all, let's talk about QAOA in the level K qubit setting. So the original QAOA was introduced by Farhi, Gutman, and Goldstone and Gutman, and its generalization to K qubits goes as follows. So first of all, we are given some function here, which we would like to maximize. And we write it as this Hamiltonian here. So basically for each string, we record its value under C, and then we project down to this X, and we sum up, and then this gives us some Hamiltonian. And for QAOA in general, what we need or what we have to choose in advance is some so-called level parameter, which we call P. And usually the higher the P, the better the approximation quality of our algorithm would be. And now the QAOA ansatz is given such as this. So we start out with the all plus state in an n-qubit qubit quantum circuit. And now we apply P layers of two unitaries. One unitary, which we get from this from our cost function or our cost Hamiltonian, and the other one is the so-called mixing term, or mixing Hamiltonian, which we define in such a way such that this all plus state here is an +1 eigenstate of this here. And so this is the exact definition, but usually the idea is simply, okay, this here should be some +1 eigenstate of this here. And then we run this. And these values beta and gamma, these are some real vectors. And so we also have to choose them. And the way this is done is we choose them by wanting to maximize the expectation value of this value C under this, if we start out with this psi state. And this can be done by, for example, gradient descent or some grid search, or in whatever technique one would like. And so for MaxKCut, we actually can write our Hamiltonian in a more general form because it's too local, which means that all the correlations are between two vertices. We can write it such as this. So we sum over all possible correlations or all possible two-point correlations and overall colors in a certain sense. And so this here are simply projectors onto the qubits I and j with whose requirements are that their values are B apart in both of these qubits. And then the MaxKCut Hamiltonian can be written in this form by choosing J in this form. And now the figure of merit, which I've already talked about, is that we want to maximize over all these angles this expectation value over C and divide it by the actual maximum value. So this is the approximation ratio. And now we already know that QAA for qubits has certain limitations applied to the k=2 case of MaxKut. And so actually we showed in our previous work that there is a certain family of bipartite deregular Ramanujan graphs such that if we choose p small enough, then the approximation ratio alpha of QAA at level p applied to such a graph of here is upper bounded by 5 over 6 plus some term which vanishes for d to infinity. And in particular, this means that if we choose p constant, then QAA is actually incapable of beating the best classical algorithm by Goemans and Williamson for the MaxKut problem. And this, so this suggests that QAA for level p for constant p is in its worst case not as good as the best classical methods. And then later on, Farhi, Germanic, and Gutman exhibited another class of functions, which were also bipartite deregular graphs. And they showed that once again, if we choose p not at least logarithmically, then in fact the approximation ratio of QAA applied to these graphs almost certainly does not even beat the random guessing. So if you recall, 1 minus 1 over k for MaxKCut was the approximation ratio of random guessing or randomly assigning colors. And then for k=2, we really only have a 50-50 chance. So in this case, it's not QAA does not even beat random guessing, which is of course very bad. And so we have to choose p accordingly large enough. And so our main result is that it basically mirrors this result by Farhi and others. And so for our, so in our class, what we have are deregular bipartite graphs on n vertices. And so this approximation ratio achieved by QAA level p for MaxKCut on G. And we have something similar. So if we choose our p small enough in comparison to n, then there are certain graphs such, there are certain parameters of n and d such that for these bipartite deregular graphs, the ratio of graphs for which the approximation ratio actually beats the random guessing goes to 0 if we let n go to infinity. And therefore, this is more or less exactly the same result just for the MaxKCut case. So basically for these graphs, this is not capable of beating the random assignment. And the proof of this result exploits two key characteristics of QAA, which are locality and uniformity. And so locality of QAA, so let's first write using linearity our expected value in this form. And now this is one interaction term. And let's focus on this one interaction term. And if we write it out and commute everything through and so on, then we see that certain terms cancel, and all the terms which are canceling are the ones which are far away from the edge that we're looking at. So for example, here, only these red edges in the neighborhood of I and j, which are at most p away from one of these vertices, actually contribute something to this term. And this is the so-called locality. So for this single term, only a very small neighborhood actually plays a role. And so it also follows from the definition that QAA is a uniform algorithm. So what does it mean to be uniform? It means that if we have two edges and its neighborhoods, which again play a huge role there, are isomorphic, then they contribute the same energy. So there is no wiggle room for that. And so therefore, it really pays off to study the types of neighborhoods that appear in a graph. And now the types of neighborhoods that we are interested in are especially these so-called trees. So the tree TPD is defined as the tree for which all these vertices except the leaves are deregular. So for example, T24 means that all non-leaf vertices are 4 regular and are at most a distance p away from the center edge. So this here is the center edge, and you will see every vertex is at most 2 away. So for example, this here. And what we will do is we will call graphs with many TPD like neighborhoods T-typical. Now, this is, of course, not a rigorous definition, but you can look into the paper for the technical details. And the key result that we need is that in order to find our class of graphs for which we try to prove our result is that if we choose p small enough, and this is captured by this condition here. And this is where the logarithmic dependence on p comes in our condition. Then almost all the graphs in almost all deregular bipartite graphs and almost all deregular graphs are T-typical, and therefore almost all neighborhoods look like these trees TPD. This is what we will use because, so for these T-typical deregular graphs, what we have is this expectation value here. So we have in total nd time over 2 edges, and we know that many of these edges look like CT, or they look like TPD, and therefore they, due to uniformity, they contribute the same value. And there is some error term because not all neighborhoods look like this tree, but this is some very small one which vanishes for n to infinity. And so from this, it also follows that for T-typical graphs, the maximal expectation value achieved by level PQAOA is roughly identical, and also that the optimal angles that we would have to choose, or these values beta and gamma, are nearly optimal. And now the last thing that we need to prove this is that for deregular graphs on n vertices, we need some bound on the expected value of the MaxKCut that actually is used there in this center. And so we know that we have an upper bound here, so the expected value, if we choose some random deregular graph on n vertices, then we have here that this 1 minus 1 over k term, which already resembles our approximation ratio of the random of the random assignment times the number of vertices, and these terms here they will vanish later, and this is a result by these authors. And now, so a very short proof sketch of the main result is now. So for some T-typical deregular graph, we show that we can actually bound this MaxKCut by this expectation value that we had here. And this means, okay, so here we have the QAOA, or the best possible QAOA bound. And we know that, well, it cannot be better than the MaxKCut, right? Because this is the absolute maximum value. And so for deregular bipartite graphs, we can always, we can upper bound this by the expectation value here, because this holds for T-typical graphs. And now we can upper bound this here due to our to the result by Koya, Oglan, and others. And then what we obtain in total is here for deregular bipartite graphs, this inequality. But now those graphs have a MaxKCut equal to nd over 2 for any k by simply choosing a bipartition. And yeah, and then if we divide by nd over 2, then we obtain here our exact approximation ratio for QAOA. And on the other side, we obtain an upper bound on the approximation ratio, which was exactly the right-hand side in our main theorem. And therefore, we've shown the claim. Okay, then let me go to the efficient classical simulation of level 1 QAOA. So as I've already said, this is another limitation. And this limitation was also already known for the MaxKut case before. So at level 1, it can actually be efficiently classically simulated. And in its most general form, what we have is we have some 2 local Hamiltonian with commuting local terms. And this here is our QAOA state for p equals 1. And the result is that we can compute these correlation functions of these local terms efficiently in a classical way. And therefore, we can, of course, efficiently classically compute the entire expectation value. And the way this is done is, so first of all, this is this correlation function. So this here would be the QAOA circuit for the complete graph on 4 vertices. So what we have here on the right-hand side first, all these empty dots here, these single qubit unitaries are the terms B beta. And now all these 2-qubit unitaries are associated with this term here, with the cost function term. And as you can see, so the complete graph on 4 vertices has 6 edges. So here we have 6 of these unitaries. And on the right-hand side, we have their adjoints. And the adjoints are indicated by black dots. And then in total, we also pinch this with the uniform superposition. And now the first thing that we see is, okay, these two here cancel because they're adjoints of each other, and therefore they're out. And now using the commutativity of all of our local terms, we can switch the terms which act only on 1 and 2 and push them to the right. Okay. And now what we can also see is if there are any terms which do not even have anything to do with our vertices 1 and 2, like these two here, then we can push them to the middle, and they also cancel because, they're adjoints of each other. And what we then see here, we can then group all of these here, and we see that for every edge that has either 1 or 2 in its vertex set, we obtain some group of unitaries that act on these. So here, for example, the third one, which acts here on the second and the first one, and so on, and the fourth one. And then what we, in the end, we can interpret this as basically a quantum channel. So we apply this quantum channel here for each. So each of these groupings here corresponds to one application of a certain quantum channel. And then the desired value is simply the probability of this output state of this application, of this repeated application, and applied to this inner term here. And this application of a quantum channel is exactly why this is classically simulable. And using that, our projectors in the MaxKCut Hamiltonian are actually commuting. We then obtain that indeed this 2-point or this correlation function, these correlation functions here are classically computed in a time which depends only on k and the degrees of the vertices that are in ij. And if all of these are taken constant, then this single term here can be computed in constant time, and therefore the computation of the entire term can be done in a polynomial amount of time because they are of an order of n squared vertices in total. And the next step is, okay, we see, okay, locality of QAOA, we've seen this in this first chapter here, is a huge problem, which leads to limitations, and we want to try to sidestep this problem, and therefore we defined recursive QAOA or RQAOA. And we did this in a previous work. And so what we have here is, so first of all, we have this cost function given here for the MaxKCut. And what we do is we are given some graph. And the first thing we do is we simply perform QAOA with some level. And we then obtain the optimal QAOA output state. And what we do now is we're not happy with with measuring the state and taking the output, but we then find a maximally correlated pair of variables. So we, for example, here we have this vertex here and this vertex here, and this one. So we calculate these correlation functions for all colors B. And then we take the vertices for which this here becomes, for which the correlation or anti-correlation becomes the largest. And we save those. And what we do then is we use a technique called correlation rounding, and we restrict, in a certain sense, to the subspace by saying, okay, this variable here will always be the value of this variable here plus this color that we have here before. And so basically we impose some constraint, and by imposing this constraint and restricting to the subspace, this last vertex here becomes like we can actually leave it out. And this is called variable elimination. And what we do is in the Hamiltonian, we eliminate all projectors which are associated with this vertex here. And then, well, what happens is we now have a graph with one less vertex. And we repeat this procedure. We once again run here QA to get an optimal state. We once again look at the maximal correlations. We once again perform correlation rounding, and then we remove the vertex. And we repeat this until the graph is small enough. Then we use, for example, brute force techniques and find a solution for the small graph. And then using the constraints that we had, we simply recursively obtain the solution to our original problem and see whether this is good or not. Okay, and now last but not least, we want to see how good does our RQAA perform in terms of actual performance to the simulated version of level 1 QAA and the best classical algorithms. And so what we've done here is we have not used any quantum devices or whatsoever. We have simply used the fact that we can classically simulate level 1 QAA, and therefore we can also classically simulate level 1 RQAA for MaxKCut. So we compare level 1 QAA with level 1 RQAA, and we compare it to the best classical approximation algorithm, which is the one by Newman for MaxKCut. And this is a randomized algorithm. And what we've done here is we have run this algorithm 100 times, and we've taken the best guess and compared this to QAA and RQAA in order to get a fair comparison. And we performed these experiments on for different parameters of n and d on 20 deregular 3-colorable connected graphs. And we actually managed to get up to around 300 vertices in this ensemble. And then we see what happens there. So this can be a bit much in the beginning, but let me briefly break down what this actually means. So first of all, this here is our plot for nd equals 306. So therefore, these are the 6 regular graphs with 300 vertices. And for each of these instances, so we had 20 instances, we now compare QAA with RQAA and with Newman's algorithm. And so for QAA, which is this magenta color here, the approximation ratio is quite constant at 0.8. So the output of QAA is roughly 0.8 times the actual maximum value, which for these deregular graphs is, of course, actually is, or it actually satisfies all the edges. And so this is for QAA. For RQAA, what we see is we actually achieve quite a bit higher approximation ratio of 0.95 or so for all of the instances. So this actually beats out QAA, and this is something that we've consistently observed for all of our examples, that RQAA is better than QAA. And for Newman's algorithm, so these blue bars indicate the best guess. And we see that for these parameter values, actually, the best guess is worse than RQAA. And the reason for this is, or one explanation for this is that Newman's algorithm has a very low variance, which is indicated by these error bars here. In terms of performance, and very low variance obviously implies that the best guess is not that far away from the expected value. And the expected value of Newman's algorithm is indicated by this orange line here. And for this regime, RQAA actually beats out Newman's algorithm in practice for this ensemble of graphs. However, there are also other, so for example, here, if there are other parameter values, so if we change n to 60 and let d stay equal to 6, then we still observe that QAA has, again, an approximation rate of 0.8. RQAA is, well, something like between 0.9 and 0.9 or 5, or here it actually achieves the maximum. But Newman's algorithm has such a large variance on this type of graphs, such that the best guess actually perfectly achieves the solution. So therefore, in this case, Newman's algorithm does not beat is better than RQAA, at least heuristically, and we're still trying to figure out what exactly are the conditions on N and D such that this happens. Okay, and in summary, so what we did is we showed that QAOA applied to the MaxKCut problem exhibits similar limitations as the original. We then showed that level 1 QAOA can be classically simulated, which is also the case for the qubit version. We extended our definition of RQAOA in a previous work to MaxKCut, and we performed some numerical experiments in order to compare level 1 QAOA with level 1 RQAOA and the best classical method. And we see that there were certain regimes in which RQAOA is actually very competitive with these best classical methods.